Okay, morning. Let's start the lecture. Okay, so let's take a quick review as to the previous lecture, linear quadratic optimal control. Okay, basically we have our dynamic system at here. Okay. So what we want to do is we want to minimize. This is basically our constraint. And we want to minimize a cost function g equal to one half x of n transpose s x of n plus 1/2 up to n minus 1, k equal to 1, x of k transpose q, x of k plus u transpose k r u of k. Okay, so and what we did is we did a little simplification. Basically, we combined the term together, assuming that s and q are the same. Okay, and we use Lagrange multiplier. Basically, we come up with an augmented cost function, and so that augmented cost function one half at here, x of k here, q x of k plus u of k transpose by r u of k plus this Lagrange multiplier, right? Then multiply by the constraint. Okay. So this is basically the new cost function. Then in order to find the optimal value x of k and u of k such that the g of a is minimized, then what we need to do is we need to basically calculate 3 partial derivative. So let this guy equal to 0 and let this guy equal to 0 and let this guy equal to 0. Okay, so 3 partial derivatives. So we play with the three equations, okay, from the 3 partial derivatives, and we come up with the final, basically final result that we come up with is, I'll just write it here. So here's what we come up with. Our u equal negative v transpose h transpose p g x of k, and v at here is r plus h transpose p of k plus 1 and h. Okay, so that's the u here. And for the p, for the p at here, it's basically coming from the discrete Riccati equation, which is the backward discrete Riccati equation. So G transpose P of k plus 1 minus P of k plus 1 and H V transpose HT P of k plus 1 by G by Q. Okay? So this is the discrete Riccati equation at here. And if you deal with a continuous system, you will have a continuous system. There's also a Riccati equation. Okay. So in order to obtain this U at here, so this U, if you look at this U at here, a U basically takes the format of this. So negative k, small k, let's to differentiate that, of this. Okay, so the U of k basically takes this format. And this k, that's essentially equivalent to k as we have been learning or designing in the pole placement control, right? In pole placement control, you find the feedback k by giving the desired pole locations. And here, this k is defined through what? Through this minimizing the cost function, right? So basically, you find the same kind of k matrix, but just through different approach. So if I write the k here separately here, so what's the k? So the k equal to, I'll just write this term, write it out here, okay? This one here. So this is a k here, okay? Ultimately, when you think optimal control, you know, by going through all of these different kind of derivations, ultimately what you deal with is these two equations. Okay, these two equations. If you do programming, and in terms of programming, just 2 lines of code. That's it, right? That's basically optimal control. So what we'll be dealing with here, okay, there's a limited value n at here, right? N value here. So basically what we're dealing here, this is called finite horizon or finite optimal control here, okay? Yeah. So of course you probably say, oh, is there the infinite? Yes. So if you change the n to infinite, then it'll be the infinite horizon here, okay? So before we move on here, so let's take a second look at this one here, okay? This P matrix or this Riccati equation at here, you can play with this equation using linear algebra. So this discrete Riccati equation has slightly, okay, a couple of more, okay, different formats. Okay, but they all the same thing though. Okay, you just can express that with a different format here. So I'm not gonna derive that anymore. In the lecture notes, I did give this one here. So which is this basically on this page here. Okay, so basically this guy. So this is one formality at here. So the P matrix, just paste it here. That's one thing. And this is another one. This one, yeah, this one is different from. This one is what. Yeah, this one is what I written on the. This one is written at here. Okay, this one is this. So you can also use this one, okay, as this discrete Riccati equation. So basically, they're all equivalent. All right. Yeah, linear algebra, they can derive that. So ultimately, when you implement this thing here, when you basically implement 2 things. So let's take a look at an example. Okay, so let's see an example right here. Now this example, in terms of writing the example, it's not that. So I'll give you a scalar system. Okay, so let's say I'll give you a scalar system in here. Alright, and let's say, assuming that initially x of 0 is 1. You know what, this, I don't know why I gave you those ridiculous number here, so maybe, yeah, let's try as integer numbers here, okay? So let's say 0.4 and 0.6. Okay, yeah. Okay, so this is a scalar number, but it's in the format of the discrete system, right? Yeah, it's not a vector, scalar. So what we're doing, that's to determine an optimal control U, okay, and such that this index at here is minimized. So the index J, the performance index J, is x of 10 to the power square plus 1/2. 9 at here, k equal to 0, x square of k plus u square of k. Okay. So let's go over the process at here, okay, and see what happens. Okay. So inspect this performance index at here, right? Let's see how does that look like compared to what we've been doing. Well, basically in this case, the S and the Q is the same thing. The N, capital N is what? 10, right? Yeah. So because this is scalar here, so that basically is 1/2 x transpose 10 by 1 by x 10, like this, right? Yeah, it's the same thing. So scalar transposes itself, so that's why I get x squared here, right? Yeah. Okay, so basically S equal to Q equal to R equal to 1. Okay, yeah. Okay, so what we want to do, we want to find the optimal control. So basically, we need either use this equation for the Riccati equation, and then we use this one to calculate this gain matrix K at here, right? Yeah. But you see what happens is when you use the discrete Riccati equation, either this one or this one, this is a backward one, right? This is backward. So backward means what? Means it's not you're starting from k equal to 0. You're actually the starting value is how much? So let's see if I want to solve this p of k here. So you got to start somewhere, right? Because QGP, QGH, okay, they all known. So where should I start with this discrete Riccati equation? Backward. So which means if you give a k plus 1 here, you get a k. Which means what? If you give n at here, you get what? N minus 1, right? Yeah. So that's the backward thing here. So you have to start. So where should we start? This is n here. So what we do is we start from the n at here. Okay. So basically, you start from p of n. Okay. Start from p of n. Now p of n, if you remember in the previous lecture, when we derive this discrete Riccati equation, or when we derive those optimal control algorithm here, we had an assumption there basically that we said p of n will be, in this case it was p of 10. That will be the matrix S at here. In this case, basically matrix Q. Okay, matrix Q. So your p of n is going to be 1. Okay, it's going to be 1. So then the discrete Riccati equation, okay, the p of k. So let's see which one shall we use. I use equation number 6. Just let me double check. Yeah. So I think I tried this one at here. Okay, I tried this one. So let's see. If I use that one, so what's the discrete quadratic equation? So what's the Q value? 1, right? What's the G matrix? This guy here. 0.4 transpose, it's 0.4 times P of K plus 1. Inside here, I here is 1 scalar. H is what? 0.6. And R is 1. So 1 inverse is still 1. H 0.6 P K plus 1 inverse G 0.4. Okay, so this is the discrete quadratic equation, right? Yeah. So the probably the most complicated exercise in the exam setting wanted to do is probably scalar. The maximum will be 2 by 2, right? Yeah. So let's say, can you write down the discrete quadratic equation, right? Given a system matrix and performance index. Okay. Yeah. So do a little simplification in here. Let's see what we have. So there's 2 0.4, so this is going to become 0.16, right? 0.16. And then divided by what? By 1 plus 0.36. Like this, right? Okay, so this is your discrete quadratic equation. Then the next thing is we're gonna solve this one here. So we're gonna solve this P of K, right? Solve this P of K. So we start this side here. You start with P of n, which is 10 at here. So then you get P of 9 on this side. So 1 plus 0.16, P of 10, 1 plus 0.36, P of 10. Right? So plug this 1 at here. So use your calculator, see what you get. Oops, I don't have a calculator here. Yeah, because I changed my question here, so I don't know the answer now. So similarly, calculate P of 8. What did you get, Trevor?
P of 9 is 1.118.
How about this one? It should converge after probably 2 steps. Huh? 1.128?
Yeah.
Increasing. Oh yeah, okay. Like this?
Yeah.
And this one should be pretty close now. Yeah, 0.128. converges, right? Yeah. So if you try a few more steps, I think it'll basically the same thing. Okay? Yeah. So basically, we have a so-called P steady state. P steady state equal to, in this case, yeah. Well, in this case, actually, if you want to calculate P steady state, what you need to do is this. Basically, that's what we call when you have like infinite case. So if it's at P infinite at a steady state, so P at here will be the same as P at here. So basically means what? You can solve this P steady state equal to 1 plus 1.16 over 1 plus 6 here and SS, right? SS. So basically, what's this one here? So that's a quadratic equation essentially, right? If you simplify this equation here, simplify it, so what do we get? So multiply both sides by 1 plus 0.36 PSS, and that gives us PSS plus 0.36 PSS squared equal to 1 plus 0.16 PSS. And then do a little simplification, 0.36 PSS squared. Move this one over here, so that minus that, so plus 0.84 PSS minus 1 equal to 0. You see that, right? Yeah.
If you multiply 1 plus 0.36 PSS to that 1 there.
Oh yeah, there should be a, you're right. There should be 1 plus 0.36 here, right? Yeah. Good point. Yeah. So how does that change the things here? So that's gonna be minus 1 minus 0.36 PSS, right? So 0.84 minus 0.36 is 0.48. Yeah. So let's just think here. 0.48. Look at that. Just reverse that. Okay. There we go. So that's this quadratic equation you're looking at here, right? So solve this one here. Is you have high school stuff, and you can get PSS, but you will get two PSS value though, right? You get two. So one of them probably is a negative number, so you shouldn't take the negative number. All right? Yeah. Is that clear? So that's basically this is what we call, this is the solution. Okay, this is the solution for the Riccati equation. Okay, Riccati equation. In MATLAB, there is a function. I don't remember which one is it now. In MATLAB, there is a function. It's to solve a Riccati equation. It's probably called DARE. Okay, it's probably called DARE. So we'll open the MATLAB later, but you can basically simply, I'll show you how to program very simply to solve this whole thing. The purpose is not for the PSS. Ultimately is to get our gain matrix K. So according to the gain matrix K, which is this formula here, okay. So that's basically R inverse H transpose GT inverse, okay, P of K minus G. Is that right? Oh yeah. So I think I forgot to mention here. This is basically another equivalent expression for gain matrix. Okay. So if you use this one or the one I listed it here, you would get the same thing. Okay. You would get the same thing. Okay. So plugging everything here. R is 1, H is, how much is H again? 0.6, G is 0.4, and P of K minus 0.4, right? Yeah. So plug, what do you do? Because we have a solved P9, P9, P10, P9, P8, and P7. So basically just plug it into this expression here and solve for K of 10 and you'll get k of 10 is 0, and you will get k of 9, which is 0.6 over 0.4 divided by pk 0.9 is 1.118 minus 0.4. So what does that give us? You're going to have to use a calculator now. So that's 3 over 2, and then this is 0.128 minus 0.4, and K7. So basically, you see your K value also converge after a few steps, right? After a few steps here. Okay? So what is it equal to, Trevor? Yeah, Mark.
We should start off by using steady state value because that's the only thing that needs to converge.
Yes, you can. Yes, you can. Yeah, but right now, what happens is, pardon me? Yeah. Right now, what happens is in this kind of question, this is basically the finite horizon in here, right? And what you wanted to know is you're also interested in the intermediate steps of the trajectory of the optimal input and optimal states x of k. So we need to take a look at a few steps here as to how they transition here. But when it comes to infinite horizon, so which means is you don't care about this. You just want to know what's the optimal value, at the steady states, and that's actually what you implement when you implement optimal control there. You know what I'm saying? Yeah. So there's this is a two different school of formulation at here, huh? There's the finite horizon and there's infinite horizon. So when you implement, let's say, from an experiment, typically we implement this infinite horizon. So basically, you don't change the k. You know what I'm saying? So you just implement a constant k or steady state k right there, right? But it's a finite one. You have to change the k every time, right, at each step, so that the j at here is minimized. Can you see the difference? Right? So the difference when you change this to infinite or horizon is you look at it, that's a different cost function, right? That's a different cost function. So different cost function. If you just use a steady state k all the time for this one here, technically speaking, you're not minimizing this one here, right? You're not minimizing. Okay. So what do we get, Trevor?
We got 1.076.
1.076.
1.091. 1.092.
Already?
92.
Okay. So anyhow, it's basically getting there, right? It's basically getting there. Yeah, it's probably k of 10 is 0.
Why?
Well, you can try. Well, actually,
it's 0.9.
0.9.
If I put p of 10, because we know p of 10.
Yeah.
Which is 1.
Oh, sorry. This is not minus g. This is minus q.
Okay. So that'll change.
Yeah, that's right. Oh, what's going on here?
Changes your number.
Yeah, that changed the numbers, right?
0.176.
0.176.
0.19 or 191.
Yeah.
0.192.
Okay. Good.
There's no 1. It's all 0.
Oh, no 0. Okay. Okay. So the other thing is you know why this is 0, right? Because basically, remember what I said, the control, this will k of 10 corresponding to which one? Corresponding to u of 10, right? Corresponding to u of 10, because u of 10 is generated from k10 and x of 10, right? X of 10. So for the optimal control here, your final state in this case, your final state is which one? Your final state is 10, right? It's 10. So the u of 10, it doesn't play any basically significance. You don't need it anymore, basically, right? Yeah. So but you don't need it, and that's why this is essentially just a 0 here. Okay. Yeah. Is that good? Yeah. So you can also calculate basically what's the u of k at each step. You basically calculate u of k at each step. What's the control input? That's basically what we call, this is the optimal control input. And of course, in order to calculate this u of k here, you have to calculate the x of k. So where do you calculate x of k? And x of k has to be calculated based on the original discrete equation, right? Discrete equation. So this one here, if you calculate the results at here, that's what we call an optimal state, right? Optimal state. So I'll use a star at here. So the optimal input optimal state, it'll result with this optimal cost function by minimized minimized cost function there. Okay, yeah. So that's the typical procedure here. Okay? If you use MATLAB DLQR, so all you need to do is GHQR, and you can just let it equal to K. It'll spit out this gain matrix K at a steady state. If you wanted to know what is the Riccati equation solution, just keep a P at here and keep a E at here. The E is going to be the closed loop pole location. Basically, based on this optimal control, and what's the closed loop pole location? And that'll be the E at here, okay, in this vector. Okay, so try it out. Yeah, is that good? And I have a little MATLAB code here. You can study that as to how it's done in a very short for loop. Let me just see MATLAB lecture. This is example number 1. Yeah. Okay, so this is basically the programming at here. Okay. So this loop calculates the solution of the discrete Riccati equation, and this loop calculates the gain, and this loop calculates the state value, and this loop calculates optimal control U at here, right? Yeah. And often in time, actually later you'll see another one here. We can combine a couple of the loops here to make it a more compact. Okay. Yeah. Is that okay? Yeah. Now the only catch is this, in this case here, the S, we assume the S equal to the Q. So basically, in this case here, the S equal to the Q at here, right? Equal to the Q. So if this is an S not equal to Q, let's say here there is a let's say there is a 2 maybe at here. Okay, so which means there's S matrix equal to 2, right? Equal to 2. So all you need to do is what? Just change this S instead of Q here equal to 2 at here. All right? Yeah. Okay. So the next question is, okay, now since we're minimizing, where is that guy? Since we're minimizing this one here, okay, minimizing this one. So the question is, what would be the minimal value for this GA or for this cost function? Okay, yeah, so what would be the minimal value for the GA?
I have a question.
Yeah.
For the P of n,
Yeah.
is it always equal to S?
Yes. Yeah. So your starting point is always just the matrix, the weighting matrix S, which is associated with the state x of n. Okay. Yeah. So what is the minimum value for that GA, basically? All right. Yeah. So again, I have to derive something in here now again. Okay, so this is the boring part. So anyway, if you recall that, okay, in the previous here, if you recall that I said at the beginning, we need to calculate 3 partial derivatives, right? Calculate 3 partial derivatives. Now, the results of the 3 partial derivatives, okay, I have it in the previous one there, right? The results of the 3 partial derivative, which is right here. So one of them is this, right? One of them is this. Okay. So one of them is this, and basically, if you move this around, the q of x of k, and I had called it equation number 3, right? I called this is equation number 3 here. So maybe I can just copy and let me just copy these equations. Just copy equations over to okay, good. Okay, so where are we? Yeah, so I'll make use of the equations that are here. Okay, I'll make use of the equations. So from equation number 3, okay, based on equation number 3, we can get q of x of k here. So from equation 3, we can get q x of k, and that is equal to, let's just rewrite that, minus lambda of k plus g transpose of this. Okay, equation number 3. Okay, so let's do this. Let's come back to the g of a here. Let's take a second look at that augmented cost function. Okay, augmented cost function. So take a look at this term here. It's this multiplied by this bracket here, right? So this multiplied by this bracket. If you multiply this lambda transpose into the bracket, what do we have? We have a lambda transpose multiplied by, there's a lambda transpose multiplied by what? By g here, right? There's another lambda transpose multiplied by h at here. Okay? So this is what's going to happen here. I'm going to try to find an equivalent expression for the lambda transpose g. But what I have here is a g transpose lambda. So then what do we do is, let's take a transpose of both sides of this equation. If I take a transpose both sides of the equation, so what do we have? We have x transpose q transpose. And q, if you remember that q is a weighting matrix. What's the nature of the q? What's the nature of a q and r? You always choose the q and r as diagonal and also symmetric, right? So which means symmetric means the q transpose will be the same as the q. Okay, so when you pick the Q and R for the optimal, okay, make sure they are symmetric. And this is lambda transpose. And this guy here, transpose this guy becomes what? Lambda transpose first. And then G transpose G, 0. See, now you have this lambda transpose K plus 1 and G at here. So basically the lambda transpose G equal, move this whole everything to the other side, equal to this. Okay, so that's lambda transpose G. And if I go back to the G again, okay, I have the lambda transpose G. I'm going to replace the lambda transpose G with what I found, okay? And here again, so there's a lambda transpose H. So let's try to find the lambda transpose H again. So where do we find the lambda transpose H? Now this time we're going to make use equation number 1. See, this is equation number 1 here, right? So we can take transpose of this equation number 1 of both sides. So from equation 1, which is this equation, okay. So take a transpose of this guy, and we get lambda transpose H and equal to negative U transpose and R. R transpose, right? R transpose. Well, same thing. The R is also matrix. It's also symmetric. So you can get rid of that transpose sign here, right? So now you have this term and this term, right? And this term. So replace the lambda transpose G and lambda transpose H, right, in the GA term. Okay, in GA. Okay, replace these things in the GA. Okay. So if you replace that in GA, you will find that, okay, the GA are greatly simplified, okay, which becomes, okay, 1/2. Okay. I'll just start with 1 here. Lambda transpose it here, x of k minus lambda transpose it here, and x of k plus 1. Okay, it becomes this. It's greatly simplified. Okay. So what's good about this is you can try to expand this one here. Okay, if you try to expand, actually, if you expand, oh, actually, it should start from 0. It should start from 0. Yeah. So what do we have? 1/2 lambda transpose 0 x of 0 minus lambda 1 x of 1 plus, then the next k is lambda 1 x1, then minus lambda 2 x of 2, right? And keep going. So basically, you can see the pattern is what? So this and this will cancel, and this will cancel the next, right? This will cancel next. So in the end, you basically just end up with 1/2 0 x of 0 right here. Okay, you just end up with this. Okay. And actually, there's one more term in the end. You end up with this 1 and then plus another one, minus another one, minus 1/2 lambda n plus 1 and x n plus 1. You're in the, for this one here. But you know that this is going to be 0, so this last term, it will be gone. And all you have is 1/2 x of n, f of 0. Okay, x of 0. Okay, and lambda of k is defined as p of k x of k. Okay, that's what we did in the previous lecture. So just replace this one here. So 1/2 x transpose 0 p of k, okay, and x of 0. Okay, x of 0. P of 0. So this is your minimum value. Okay, this is the minimum value for the performance index. Okay, for this finite horizon problem right here. Okay, on finite horizon. So in the previous example, if the question here is what's the minimum value of the JA or the performance index, so what do you have to do? You just have to find the P naught first, right? Got to find a P naught, and then find X naught, plug it in, then you can find the JA value. Okay, yeah. Okay, so that's it for optimal control. Then the last point and the last 2 points I want to make is basically for infinite horizon. So basically the n goes to infinite, right? The n goes to infinite. In this particular case, what would be the formulation for the optimal control? So not much difference, right? Not much difference. For infinite here, basically your J matrix or performance index will become 1/2. This is infinite in here. So start of 0, x transpose k, q transpose x of k here, plus u of k, r u of k. Okay, so that's the j here, right? So the Riccati equation, which is either one of the Riccati equation that we've shown at here. So what do we do with the Riccati equation then? So basically you can get rid of the k plus 1 on the both sides of the equation, because we're talking about steady state now. So the Riccati equations become, let's say in this one here, p equal to g transpose bracket p minus p h and p g plus q. So that's what happened to the Riccati equation. All right? Yeah. So let me just rewrite here. And then the p, one of the form you can take is p equal to g t p g minus g transpose ph and r plus h transpose ph inverse ht and g. Okay, so that's the Riccati equation. And the k, the gain matrix K is going to be R plus HT and PH inverse H PH transpose P and G. Okay. So nothing really too much different than here. Just get rid of the K now. Okay, get rid of small k index. Okay. So let me show you an example right here. Okay, this is another example, but not infinite horizon here. Okay, just another example, but a little bit more complicated. It's a 2x2 matrix. So here's an example here. So this is a system that is 2x2. This order of system order is 2, and the cost function here goes to 50 at here. Okay, and what do we want to do is We want to check out the effect, okay, the Q and R matrix. So basically, plot find optimum gain subject to the R matrix R here when it's 0.1, 0.5, and 2. Okay, and to see what's the effect on the gain K there. So before you calculate it, as we actually discussed, what do you think will happen when you have a small r? The gain K, would that be bigger or smaller?
Smaller R, the bigger.
That's right. It should be bigger, right? Yeah, because the R restricts is on the control effort. So less R meaning you have less constraints basically on the control effort. So you can put a bigger K value. The end results actually will see that it's not that significantly big though. Okay, there's slightly change in the K. It will be bigger. Okay. So here's the formulation here. Basically, same thing. Recut the equation in the gain matrix, right? And if you look at the MATLAB code here, just 2 lines of code, right? Just 3 lines of code. So basically, that's the implementation of the discrete quadratic equation and the calculation of the gain matrix. But it's the calculation of it's inverse. Basically, started from n equal to 50, and then backwards up to 0, right? Back to 0, 0, 0. So the plotting at here, okay, is shown at here. So that should be R, R, R. So apparently, see, as R equal to 0.1 at the steady state, you have a higher value for the K here, right? For the K. Make sense? Now K has 2, okay? So there's a green one, there is a blue one. So what's the K then? Remember, K U equal to negative K by X of K here, right? X of K. If X of K is a 2 by 1, if X of K is a 2 by 1 at here, then this guy is going to be what? 1 by 2. So K, there are 2 values basically, huh? There are 2 values. So the plot at here are the plotting of the 2 values at here. Okay? Yeah. I'm not sure which one is which now, but it's the plotting of the 2 components of the gain matrix K. Okay. Yeah. So play with the function of the MATLAB there, okay? And you can use that for your calculation purpose. Okay. Okay, so the last one is actually probably for you, it's your interest, for your interest in implementation. Up to here, the implementation control is the regulator. So what do you mean by regulator? Giving initial condition, non-zero one maybe. What do you want? You want basically if you apply this one to the system, and the system will be regulated back to 0, right? So this is a regulator so far. Okay, but in more practical case, what you really need is what? Is a reference tracking problem, right? So you have the input, step input. You want to regulate, or you want to basically control the output to be the same as the input. Make sense, right? So that's basically if the next thing here it's the optimal control, okay, with a reference input, okay, with reference input. Okay. So what do we mean by with the reference input? So let me just write down the system matrix first. So here's our system model again. Okay, here's our system model. And here's the output at here. Okay. Okay, let's suppose that we're talking about a single input, single output here. I'll just get rid of the negative vector sign in here. Okay, yeah. All right. So now, if this is a reference control problem, then the performance index or the cost function will have to be slightly changed. The J, previously the J is what? Is 1/2 x of k, x of n at here, then plus a matrix S, and then plus x of n, right? And that's the regulation. You're trying to bring the x of k back to 0. So now what you do is this. You change this performance index in here. So you see the difference here? So this basically, instead of the performance index is related to x of k, you relate the J with the difference between the output and the reference input. So the R of k is reference input, okay? Okay, it's the reference input. And that's the final state. And for the inside here, y of k here, r of k transpose, then q, y of k, and r of k. Okay. That's big bracket here, plus u of transpose. This is the same thing. Okay, this is the same thing as before. Okay, so this is the new performance index. Okay, see the difference, right? That now the performance index previously relates only to the state and the control input, so that you minimize the J. Basically, you're minimizing the state value. And here it's related to the difference between the output and the reference input, and that's actually what we call what? This is the error, right? This is basically the error here. If you can bring this error back to 0, which means you have a good reference control. Okay, that makes sense, right? So that's the performance index here, right? Yeah, and of course your initial condition, okay, is x of 0. Okay, yeah. Now, in this particular case, your x of n, you don't have, because it's not inside this J now, so it's free. Well, free, not necessarily free, it's still being controlled basically, right? Yeah. So what do we do next then? You actually basically, we're not going to go through the whole boring stuff anymore. So what basically happens next is the same thing. You know, you create an augmented, using Lagrange multiplier, augmented performance index, calculate the 3 partial derivatives, manipulate them, find the discrete Riccati equation, and find the feedback k again, right? So same thing. Okay. So it's a little bit more complicated than that regulation problem. But in the end, what happens is you basically get this whole bunch of algorithms at here. Okay, you basically get this one here. So that's your implementation essentially regarding optimal control algorithm, right? And for reference control. So you should take a look at this one here. How would you implement this? Okay. Yeah. So typically you're going to have to calculate the steady state of V, steady state of P, and steady state of K first. So in order to calculate K, depends on the P. Okay. In order to calculate the P, okay, that has to be calculated. The V has also to be calculated here. Now we also have a Ki at here. That's basically an integrator term, so that you can essentially basically bring the error back to 0. Okay, bring the error back to 0. Okay, yeah. So I'm not sure why there's strange things happens here. This is a P here, and this is V. This is a C transpose S R of N. Okay. And this is C transpose S C. Okay. Okay, so implementation is not that bad, particularly if you use a Simulink and you have to offline calculate what the key here is, what the key I is, then you can implement. Okay, so we have to offline calculate this capital K, small k, and capital Ki, small k. Okay? Yeah. In order to calculate this Ki here and the k, this v also has to be calculated offline. Okay. Yeah. All right. I'll show you some MATLAB simulation in here. So sometime next week we'll start the common filter. Next month, no, next one, maybe not next week. So I'll ask you to bring your computer here so we can program that common filter Simulink module altogether. Right? Once the simulation works, all you need is just bring the module over to the lab, and then you can just implement it to the actual system. Right? Yeah. That's probably the most difficult part of the programming here. But in terms of the LQR or reference control here, those are fairly straightforward. Okay. So here, I'll show you what example here is. The example is essentially the same example for the example number 2. So basically this example here, okay, this example. And we wanted to design a reference control system for this system right here, okay, this system. And there are 2 different programs in program here. So open this one here. Yeah. So there's a script file, okay, for this one here. Yeah. So you can see the system matrix GHC, and that's what's happening here. The sampling time is 0.1. Okay. So what do we do next? We basically need to offline calculate what the k and the ki is, right? See this portion in here? That's the calculation of n. So I give an n value which is a 50. See it, right? In that example here, the n is 50 at here. Okay? Yeah. And we calculate, okay, the loop. This loop right here is to calculate the k, ki, and p, then the discrete quadratic equation p, and the v matrix, which is this one here. Okay. If you look at the expression in the M file, which is actually the algorithms over there. Okay. Yeah. Ultimately, when you do the implementation, what you can do is, okay, just check out what's the steady state value of those k, ki, and p, and v. Just check out the steady state value, all right? Because that's actually when you implement, that's the steady state value is the one that you're going to use. So ultimately, when you implement, you're not really implement a finite horizon. You're implement as a infinite horizon. You're going to run the experiment forever, right? So all you need is you need the steady state value of those values that are here. And then just plug it to the U and then calculate the response of the system. Okay? Yeah. So if I plot this thing, if I run it, okay, so that's what happens there. What's the second plot? YKK. What's YKK? Oh, yeah. So the YKK is the second state, which is the velocity, suppose. So get back to 0, right? And the first one is the first state's response. I'm giving a reference input. Basically, it's all 1, so you can see that essentially goes to 1. Okay, right? So it runs for 5 seconds here because 50 times sampling time 0.1 is 5 seconds, right? 5 seconds. Okay, yeah. So study this example here. Okay, get a feeling of how would you implement the reference control, optimal reference control. All right, yeah. I believe I have another one here. Let's just see. Yeah, there's another one. This is a different system. You can take a look at this one here. Okay, this is a different system. This is a third order system. Okay, yeah, this is the kind of system. This is actually one of the assignment when I was studying control courses. Forget which one is it now. And that's the basic assignment question and the programming, and that's my solution there. Okay, yeah, it's done in 1998. And believe it or not, it still runs. Yeah, so this is basically the responsive system, right? Yeah, so check out this one here. Okay, it's just an equivalent basically as to what I showed you there, right? So check this. But I need you to consider what I need you to consider is this. Okay, consider is your focus is at right now when you do exercise, finite horizon is okay, but you need to focus on how would you implement this. Okay, basically implement the reference control. So let's say I have a sinusoidal input to the system. Under the LQR control, the response should be a sinusoidal, right? Should be a sinusoidal too. If you give a step input, it should also be a step input. So implement to the regulation problem is easy, right? But implementing the reference control is more of a practical case. Make sense? Yeah. So as I said, you have to calculate those offline first before implement the block. But ultimately, when you implement reference control, okay, all that happens is, okay, in terms of block, you just need two blocks. One block is the ki, and the other block is the u is the k. So basically, when you implement, you only need two gain blocks, right? The whole question is what will be the value of the two gain blocks. As a matter of fact, even you calculate wrong, if your optimal control you calculate wrong, you put the wrong value here, and it probably still works. It's just not the optimum control, right? Yeah, so that's the key point here. Okay, so I think I'll stop here. It's going to be a big deal for you guys, right? And the last assignments, well, only 4. So the last assignments is going to be optional. So basically, that you don't need to submit it anymore, and it's not going to be counted for the grades. So the first 3 assignments will be okay, right? Yeah. I'll post the last assignments. A part of the last assignments basically ask you to do simulation. To do simulation on the model that I give it to you, experiment model. Simulate LQR, simulate the pole placement, simulate common filter that we're going to learn, simulate the PID, right? And those things basically is going to be a part of your project report. Okay? Yeah. Any questions? Good.